the machine under London that keeps the city running. At first light, London looks almost still. The Thames moves beneath bridges, buses begin to fill, office lights blink on behind glass. But the city has already been awake for hours. Far below its streets, inside tunnels most Londoners will never enter, a second city is working. It has no mayor, no skyline, and no single control room. It is made of railways, sewers, water mains, pumping stations, power cables, service tunnels, and data lines. It moves people, clean water, wastewater, electricity, and information through one of the densest urban landscapes on Earth. When it works, nobody thinks about it. A train arrives, a tap runs, a phone charges, a toilet flushes. The city feels ordinary. But this ordinary life rests on a hidden agreement that millions of separate systems will keep moving at precisely the moment they are needed. And London learned the price of breaking that agreement the hard way. Before the great tunnels and modern control rooms, London was a city growing faster than it could protect itself. During the 19th century, the capital expanded at a staggering pace. More people meant more homes, more workshops, more waste, and more pressure on a river that already sat at the center of the city's life. The Thames was London's trade route, its landmark, and, increasingly, its problem. Waste entered the river. Drinking water was drawn from the same polluted system. In the crowded districts, disease spread with terrifying speed. Cholera outbreaks killed thousands of Londoners. For years, the crisis was tolerated because it was complicated. Responsibility was fragmented. Money was scarce. The work would be disruptive, and the scale of the necessary solutions seemed almost impossible to imagine. Then came the summer of 1858. The heat was intense. The Thames became a foul-smelling symbol of failure. The stench was so severe that it reached Parliament itself. What became known as the Great Stink turned an invisible sanitation problem into a national humiliation. London could no longer pretend that the river would absorb everything the city sent into it. The man who would help change the city was Joseph Bazalgette, chief engineer to the Metropolitan Board of Works. He was not selling a simple fix. He was proposing a system, intercepting sewers, pumping stations, embankments, and drainage routes that would gather waste before it reached central London's riverfront. It would be expensive. It would disturb streets and businesses. It would demand an enormous amount of brick, labor, and political will. But Bazalgette understood the central truth of urban infrastructure. A city cannot solve a city-sized crisis with a collection of small, disconnected repairs. The project also required London to accept an uncomfortable idea. The city had to pay now for benefits that would be felt later, often by people who would never know the names of the engineers or laborers responsible. That is the aphilos, strange politics of infrastructure. Its cost is immediate. Its success is usually anonymous. Bazalgette designed with room to spare. His sewers were larger than many contemporaries believed necessary. That decision looked excessive to some people at the time, but it gave the system resilience as the city expanded. It was not a guarantee against future pressure. It was a reminder that the cheapest system is not always the one that survives. The scale of the work was almost industrial warfare turned inward. Streets were opened. Brick kilns worked. Laborers dug, laid, and sealed. Pumping stations rose at the edges of the expanding metropolis. The project reshaped the riverbank and forced the city to coordinate public works on a scale it had never attempted. London was building a defense against a threat that had no army, no flag, and no single battlefield. That mattered because sanitation was not only a technical question, it was a question of power. Wealthier districts could sometimes shield themselves from the worst consequences of polluted water and overcrowding. Poorer districts could not. A city-wide sewer system did not erase inequality, but it recognized that disease, water, and waste crossed the boundaries people drew for themselves. His plan carried sewage eastward, away from the crowded center. It built major pumping stations. It transformed parts of the riverbank. The Thames embankment became a famous public work, but its grandeur concealed a more practical purpose. Behind and beneath it, infrastructure was being built into the city itself. The result did not make London perfect. It displaced problems downstream and required later generations to continue improving the system. But it changed the city's relationship with disease, waste, and public health. The hidden network became a backbone for modern London. That backbone still matters. Yet the London of Bazalgette's time has vanished. The city grew beyond the scale he could have known. More homes were built, more streets were paved, more rainwater was channeled into drains. More people depended on a network designed for a very different century. In a combined sewer system, wastewater and rainwater can share the same roots. During heavy rainfall, the volume can become too great. Overflow structures are designed to prevent sewage from backing up into homes and streets. Historically, this meant that overflow could enter the tidal Thames. The modern answer is another tunnel beneath the river. The Thames Tideway Tunnel runs 25 kilometers from west to east London. In places, it lies as deep as 67 meters below ground. It is 7.2 meters wide, roughly the width of 3 London buses. The tunnel is not a replacement for the Victorian system. It is an extension of it. It intercepts storm flows and carries them toward treatment infrastructure farther east. Old brickwork, modern concrete, pumps, sensors, and treatment works now operate as parts of one larger network. The tunnel's existence also reveals the limits of nostalgia. Victorian engineering is rightly admired, but admiration cannot make an old system carry unlimited growth. London has to preserve what still works, understand where it no longer works, and invest before a visible crisis forces its hand. That is less dramatic than a grand opening ceremony. It is also more difficult. This is London's real pattern. Its old systems are rarely discarded. They are connected, reinforced, rerouted, and monitored. The city survives not because it was planned perfectly from the beginning, but because it is continually repaired. Water is the clearest example. Turn a tap and clean water appears. Pull a plug and it disappears. Between those two actions lies a chain of rivers, reservoirs, treatment works, pumping stations, mains, drains, sewers, and laboratories. Thames Water says it supplies more than 2.6 billion liters of water every day across its customer area. Much of that water comes from rivers. Some comes from underground aquifers. Before it reaches a home, it must be treated, tested, stored, pressurized, and moved through a vast network of pipes. Then the water begins its return journey. From showers, kitchens, offices, restaurants, and hospitals, it enters a sewer network spanning London and the Thames Valley. Gravity carries some of it. Pumps move it where gravity cannot. Treatment works receive it at the end of a journey most people never consider. The system is not simply a set of pipes pointing downhill. It is a controlled sequence of bottlenecks, valves, pumps, and decisions. A blockage in the wrong place, a burst main or a severe storm can turn something invisible into an emergency everyone can see. Even the water itself has competing demands. Households need it. Hospitals need it. Businesses need it. Industry needs it. Green spaces need it. The same city that fears flooding during a storm can worry about drought during a long, dry period. Managing water means planning for opposite dangers at once. The source of water is only the beginning. Treatment must remove harmful material. Reservoirs and storage must balance demand. Pressure must be maintained across neighborhoods of different heights. Leaks must be found in a network that is often buried under crowded roads. Every liter that reaches a tap has already passed through a long chain of engineering, testing, and judgment. This is why a water system is never a finished object. It is a service performed every day. It must respond to population change, new buildings, weather, repairs, and sudden demand. The pipe is only the visible part of the promise. The real system includes people, plans, laboratories, spare parts, and the ability to respond when conditions change. The difficulty is made greater by London's density. Beneath one ordinary street may lie a Victorian sewer, a water main, a gas pipe, power cables, fiber optic lines, building foundations, and a railway tunnel. Every new construction project has to negotiate with the accumulated decisions of the past. That is why workers increasingly need detailed maps of what is below the ground before they dig. A mistaken excavation can damage a cable or main, disrupt a road, and create consequences far from the hole itself. Beneath London, the empty space is often the rarest resource. Then there is the tube, the most visible part of London's hidden city. Transport for London's Underground has 11 lines, 272 stations, and 402 kilometers of route. On its busiest days, it handles up to 5 million passenger journeys. Those figures describe a transport network. They do not capture the constant choreography beneath the surface. Every train depends on power, signaling, ventilation, track maintenance, station staff, escalators, communications, and timing. A platform is not simply a place where people wait. It is a controlled exchange inside a moving system. During the busiest moments, that exchange becomes a question of seconds. Let too many people arrive at once and a platform becomes unsafe. Hold trains too long and pressure builds elsewhere. Send one train into the wrong gap and the delay travels down the line. The Underground is a machine of movement, but also a machine of managed waiting. Its history is written in layers, too. Some lines were built by competing private companies. Some tunnels were made for a city of hats and horse-drawn traffic. Modern stations and systems have been added around them. The famous diagram on a tube map makes the network look clean and simple. The physical network beneath London is neither. It bends, narrows, climbs, descends, and shares space with systems that have their own histories. The tube demonstrates a wider truth about infrastructure. An elegant public experience can conceal extraordinary complexity. A passenger only needs to know a platform, a direction, and a stop. Behind that simplicity are timetables, safety rules, repairs, operators, energy supplies, and contingency plans. The better the system performs, the less its users need to understand it. The underground also competes for room. New tunnels must avoid foundations, sewers, cables, old railway tunnels, and the river itself. A route is not drawn through empty earth. It is threaded through a dense archive of earlier construction. Electricity is equally essential. London does not generate most of its power on the streets where it is used. Electricity arrives through the wider grid, passes through substations and branches into stations, hospitals, homes, offices, shops, and data centers. The flow seems instant. The infrastructure is not. A tube station needs lighting, signals, escalators, and ventilation. A hospital needs dependable power for critical equipment. A payment terminal needs power and data. A traffic junction needs power, communication, and maintenance. 1. Network's interruption can quickly become another network's crisis. This interdependence is the real machine beneath London. Water relies on electricity for pumps and treatment. Transport relies on electricity and communication. Buildings rely on water, drainage, energy, and data. The city is not a collection of separate systems. It is a chain of promises. That chain also explains why resilience matters more than perfection. No system can prevent every fault. Pipes age, equipment fails, weather changes. What matters is whether there are alternatives, trained people, clear information, and enough capacity to recover before a small fault becomes a wider breakdown. Resilience can be unglamorous. It may mean a second cable route, a spare pump, a reservoir margin, a maintenance inspection, or a map shared between organizations. None of these things makes a memorable landmark, yet they decide whether a city absorbs a shock or passes it from one system to the next. Those promises are kept by people working beyond public view, in control rooms, rail depots, pumping stations, cable tunnels, inspection shafts, and treatment works. Most of their work is preventive. They inspect, clean, replace, test, measure, and plan so that a dramatic failure never becomes necessary. That labor is difficult to celebrate because its success is absence. No flood, no smell, no delayed train, no burst pipe, no blackout. A city judges infrastructure by what it does, not force people to notice. There is a human cost to that invisibility. The people who maintain the city are often noticed only when something goes wrong. Yet the quiet work, clearing a blockage, replacing a worn component, checking a signal, inspecting a tunnel wall, is what prevents the dramatic moment from arriving in the first place. Their work is also constrained by the same city they protect. Repairs must often happen overnight, when roads are quieter and stations are closed. Equipment must fit through narrow access points, work near electricity, railways, water, or confined spaces demands specialist safety procedures. The city does not pause while it is repaired. Maintenance has to coexist with movement. That is why disruption is sometimes the visible price of reliability. A closed lane, a station upgrade, or a temporary diversion can feel like failure from street level. Often it is evidence that the hidden system is being taken seriously before it fails at a worse moment. But London's underground machine is under new pressure. A changing climate means heavier bursts of rain, hotter weather, and more uncertainty around water. Electric vehicles, heat pumps, and data centers increase demand for energy. New homes need new connections. The city must modernize while millions of people continue to depend on yesterday's systems. That is why London keeps building below ground, new electricity tunnels, water resilience projects, rail upgrades, and utility coordination schemes are not evidence that the old city failed. They are evidence that a living city is never finished. The challenge is not only to build more, it is to build without breaking what already works. Every new route is a negotiation between geology, history, ownership, safety, cost, and the needs of people above. You can redesign a website overnight. You cannot redesign a 19th century sewer, a railway tunnel, or a power network without confronting the physical city. And nobody owns the entire machine. Different organizations operate water, transport, energy, telecommunications, roads, and buildings. Coordination is therefore not a luxury, it is one of London's basic survival skills. Coordination has become more important as the underground grows more crowded. A road open to repair one utility is an opportunity for another provider to inspect or replace something nearby. Shared planning can reduce repeated disruption. Shared data can reduce accidental strikes. But cooperation is difficult because organizations have different budgets, responsibilities, and timetables. The city works only when those separate incentives are made to meet. There is no final blueprint waiting to be completed. London will keep changing, and the demands placed on its hidden systems will change with it. The next great infrastructure project may be a tunnel, a treatment plant, a power upgrade, or something less visible, a better way of coordinating what already exists. The principle will remain the same. The city must plan at the scale of the systems that sustain it. When that coordination works, the public sees an ordinary street. When it fails, people see roadworks, broken services, delays, and disruption. The hidden work is judged by what never happens. This is why infrastructure is so easy to underestimate. A landmark announces itself. A repaired water main does not, but the repaired main may matter more to the daily life of a neighborhood than a building seen on every postcard. London's greatest machine is not a single building, train, or tunnel. It is the agreement beneath all of them that hidden work will continue tomorrow and that the city above can trust it to. Tomorrow morning, millions of people will descend into stations, make coffee, open shops, take showers, send messages, and turn on lights. Each action will be small. Together, they will place an immense demand on a city beneath the city. Water will keep moving. Pumps will keep working. Signals will keep separating trains. Cables will carry power. Crews will inspect what needs inspection. And the hidden London will continue doing the work that allows the visible London to exist. That may be the real definition of a functioning city. Not a skyline, not a landmark, but a set of systems resilient enough that millions of strangers can depend on one another without ever meeting. Next, we go to Singapore, an island with little room, no margin for waste, and one of the most ambitious water systems ever built.